Hello and welcome to another WJEC A level physics question. This time is question 4 from June 2009's PH5 paper. It's on magnetic fields, which is currently in Unit 4. For the first part of the question, we've got a wire that's carrying a current of 4.9 amps, and we've got to use the equation B equals mu naught I over 2 pi A to calculate the flux density at point P. So mu naught is 4 pi times 10 to the minus 7. Current is 4.9 amps over 2 pi times 3.2 centimeters, so don't forget to turn that into meters. Quick tip here, cancel a 4 pi and a 2 pi to give a 2 on the top, because sometimes you can get difficulties when trying to type into your calculator 4 pi times 10 to the minus 7, and this avoids that difficulty. That gives us a value of 3.06 times 10 to the minus 5 Tesla. Now we're asked to give the direction of the field as well. To do this, we're going to use the right hand grip rule. Point your thumb of your right hand in the direction of the current, so line your thumb up with the wire with your thumb pointing up the page. Your fingers curl as if you've made a fist, and at point P you should find that your fingers are curling into the page. For part B, an electron passes through point P, moving at 7.2 times 10 to the 6 meters per second, and we've got to calculate the force experienced by the electron. So we can use F equals BeV, or technically BeV sine theta, but the sine theta bit here will be 1. So we can put in B of 3.06 times 10 to the minus 5, E as 1.6 times 10 to the minus 19, the electron charge, and V is 7.2 times 10 to the 6 meters per second. Putting those figures into the calculator allows us to come up with an answer of 3.5 times 10 to the minus 17 newtons. And we've got to give the direction, so this time we're going to use Fleming's left hand rule. So remember that the first finger represents the direction of the field, that's into the page. Your your center finger represents the direction of the current. Now electrons are negative charges, and the direction of a current is defined as the direction that positive charges move. So what we're going to do here is point our center finger downwards because the electron is moving upwards, and then you'll see that your thumb is pointing to the right, and that's the direction of the force on the electron and hence the direction of its motion. For part C, we've got to calculate the force per unit length experienced by the middle wire in the arrangement shown. Well, if we use the right hand grip rule, the field due to the left hand wire will be into the page, so I'll mark that and call it number 1. And similarly, the field due to the right hand wire will also be into the page, so I'll mark that as number 3. So those two fields being in the same direction are going to add up. The individual fields were 3.06 times 10 to the minus 5 Teslas. So B total, the total field at that point, will be 2 lots of 3.06 times 10 to the minus 5. And that will give us 6.1 times 10 to the minus 5 Teslas. Next, we can use the expression that the force on that central wire is F equals BIL. Again, technically there's a sine theta, but because of the perpendicular directions, the sine theta will be 1. But we're not asked to find the force, we're asked to find the force per unit length, so we're asked to find F over L. F over L then is B times I, so 6.1 times 10 to the minus 5, times the current in that center wire. We've already used the currents in the other two wires, which will give us an answer of 1.2 times 10 to the minus 4, and the units will be newtons per meter. Thank you very much for listening. Please remember to like and subscribe, and feel free to leave any comments. Goodbye.